Hey, welcome back to our lecture on list comprehensions. And what we're going to do in the second part is talk about a function called zip that we can use to combine two lists into a single list. And here's the signature for zip. So zip has type list of A to list of B to list of pairs of A, comma B. And here's an example of zipping two lists together. And there you can see why this function is called zip. It takes two lists, and it takes each value and combines them in a pair. So zip of A, B, C, and 1, 2, 3, 4 is A1, B2, C3. And the zip stops as soon as one of the lists is exhausted. So in this case, you see there's 4 elements on the right list, but only 3 elements on the left list. And the resulting list has 3 elements. As I mentioned in one of the earlier lectures, I think the signature of zip would be a little bit nicer if it was not curried. So if you would write pair of list of A, list, comma B, to list of pair of A, comma B. But this is just the way zip is defined in the Haskell standard library. Using zip, we can define the following function that takes a list and creates pairs of every adjacent value. So if we have, let's first look at the example down here before we look at the implementation, because I think when you see the example, the implementation is fairly obvious. So what we want to do is, given 1, 2, 3, 4, we want to kind of create a chain, like a sliding window of pairs, 1, 2, 2, 3, 3, 4. So you see that, you know, the 2 is chained there. It's like 1, 2, 2, 3, and then 2, 3, 3, 4. So how can we do that? And this function here is, I think, a beautiful example of using zip to do this. So what you do is I take that list, 1, 2, 3, 4. Then I take the tail of this list, 2, 3, 4. And then I zip those two together. So now what we get is, since we start, the first list is 1, 2, 3, 4. And the second list is 2, 3, 4. So now when we zip it, we get 2, 3. And then when we zip the next one, we get, when we zip that, we get 1, 2. The next is 2, 3. And the next is 3, 4. All right, so if you would draw the picture, you get the list. You drop the first element, you shift it one up, and then you zip the two. And this is exactly what you get. All right, here's another function that uses the function pairs to check whether a list is sorted. So what we do is we take all the adjacent pairs in the list, so that will give us, x, y's, and then we check that the first value is smaller than the second. So a list is sorted if we look at every adjacent pair of elements, the first one is less than the second. So this is a super concise way to check whether a list is sorted. So let's just look at some examples. Is 1, 2, 3, 4 sorted? Yes, it is, because 1, 2, 1 is less than 2. Then the next pair is 2, 3, 2 is smaller than 3. And the final pair is 3, 4, where 3 is less than 4. So that list is sorted. Is 1, 2, 3, 2, 4 sorted? No, because the second pair in pairs of this list is the pair 3, 2, and there 3 is greater than 2. So that will return false. Using zip, we can also define the positions of an element in a list. So as I mentioned before, lists don't have any position, unlike arrays, where in an array you can index into the array. With lists you cannot. With lists you can only access the elements from left to right. So I can take the head, and then the head of the tail, and then the head of the tail of the tail, etc. But sometimes it's convenient to also have the position of each element in a list. So this is a fairly common operation. And the way we do that is using zip. So what we do is we take the list, x's, we take the list from 0 to n, where n is the length of this list, but this really can be the infinite list starting at 0. And then we just zip the list with the positions to get every element here. All right, so if we look at the positions here, we get the positions of 0. Well, those are these, and these. So what we did is we first zipped every element with its position, and then we filter out only the values that we were looking for, because here we're only interested in the positions of 0. And so this thing goes in 2 steps. We first pair every element with its position, and then we filter out only the values that we were looking for up there. In Haskell, strings are nothing more than syntactic sugar for lists of characters, which means that you can use comprehensions over lists as well. So for example, here's the string ABC, which is really nothing more than the list of characters A, B, and C. And hence, all operations on list, including comprehensions, but also map, filter, fold R, all the list operations that we will see will work over strings. For example, the length of A, B, C, D, E is 5. And why is that? Because that string is just a list of 5 characters, and so this uses the length function over list. We can take the first 3 characters of a list by using take 3, so we get ABC, and we can zip a list, a string with a list in this way. So for example, if we zip ABC with 1, 2, 3, 4, we get the list of pairs with the character A, 1, character B, 2, and character C with 3. And many other languages also have strings implement, iterable, or enumerator, so you can do the same thing. But in Haskell, really, there is no special type for list. It's defined as a list of characters, and the only thing is that there's a special literal syntax, just like the syntax for lists really, as we have seen, means 1, const 2, const 3, const 4, const on the empty list. Here's an example where we can count the number of lowercase characters in a string. So what we do is we say, give me all the characters X in a string X's, filter out all the ones that are lowercase, and then compute the length. So for example, if we count the number of lowercase characters in the string Haskell, we see that there are 6, 2, 4, 6, and then the first character is an uppercase symbol. All right, hopefully you've got a little bit of a feeling of list comprehensions, zip, and the fact that strings are lists. And in the exercises, there will be plenty of opportunity to practice with that. See you next week. Bye-bye. Happy hacking.